To help make decisions using decision trees, we want to look at the different possible outcomes that are represented here in our decision tree and look at the expected monetary value that comes from the different outcomes, recognizing that there's a probability of each event occurring. So to solve a problem using a decision tree, we need to look at all the possible routes. So if we're looking at this one here, we can see that one route is just to immediately terminate A0 to A2. One is to go from A0 to A1 to A4, that ends it. A0 to A1 to A3 to A6, and A0 to A1 to A3 to A5. So we have 4 possible outcomes here. And so what we want to do is we want to create a table containing the probability and the values from the decision tree. So we start first with a table that has the list of activities and the probabilities and values from that. And then we'll also create a list of the possible routes. Once we do that, then what we can do is calculate that expected monetary value, which is going to be the weighted average of the possible payoffs. So for example, the A1 to A3 to A5 route, A1 to A3 to A5. So we invest in R&D, we do marketing, and it's a positive economy. Then in that case, we have invested $10,000 plus the $5,000 for the marketing campaign. So we have spent negative $15,000. And then when we go to sell it in a positive economy, we will get from that 3,500 times 35. So when you combine these three, negative 10,000 plus a negative 5,000 plus 3,500 times 35, the money we would make from that route is 107,500. The probability of that route occurring is the 30% chance we invest in research and development, the 60% chance that we go to marketing, and the 40% chance that we have a good economy. So we take 0.3 or 30% times our 60% or 0.6 times our 40% or 0.4, and you get that the probability of us ending up on that route is 7.2%. So we would look at the different possible routes and find their value and their probability, and then we can find the expected monetary value by looking at the total value we would make off of all these combinations. So let's take a look at how to do that in Python. All right, so we are in the optimization workbook, and in another video we created our decision tree here. If you are working along with us, we are at drstephpowers.github.io/BIA, and you can find it here, right here, this button called optimization, because we are doing prescriptive analytics. We are looking at what should the organization do. In this case, should the organization do R&D? Should they do marketing? Given that there's uncertainty, the economy might be good or bad. So we're looking at making decisions when there is uncertainty. To run this in Python, we're going to import pandas as PD and NumPy as NP. And then we're going to specify our assumptions here. Our assumptions here are that the price that we're going to sell it for is $35. And that if it's a good economy, we are going to sell a quantity of 3,500. And if it's a bad economy, we're going to sell 1,400. Now, the reason we've put this here at the top is because in our future videos, we'll look at sensitivity analysis. So how sensitive is the decision we make to the assumptions that we make? Maybe the price that the market says the product is worth is going to be different. Maybe the good economy, bad economy is going to be different. And so we'll later run tests to see if we change those quantities or change those prices, what happens to our decision. So let's do it right now with those being set. So we'll set those assumptions here. And then what we're going to do is we're going to create that table just as we were talking about before. So let's step back here. So first, let's create a table of the activities and the probability of them occurring and the value or the cost or benefit when they do. So let's go in here We're going to create a list called activity, A1, A2, A3, A4, A5, A6, because A0 is given. That's where we start. And then our probabilities here, 0.3 and 0.7, that was between doing research and development, 30%, terminating was 70%. You'll recall from that tree. So let's just go back to our tree. That's this branching right here. And then we have this branch here with 4 and 3, so 40% and 60% for that one. So that's this 60% and 40%. And then we have here, oh, wrong thing. Then we have here, this last choice here, is it a good economy or a bad economy? 40% chance of good, 60% chance of bad, and the amount we will make, the revenue we will make from selling the product is the price, $35, times the quantity, and the quantity, remember, is going to be different if it is good or bad. So we'll put in our probabilities here, 0.3 and 0.7, 0.6 and 0.4, 0.4 and 0.6. Those line up with the decision tree we created. And the values correspond the same. There's a 30% chance we do research and development. It'll cost us $10,000. If instead we terminate the plan before we invest any money, it costs us $0. There is a 60% chance, let's just double check that that's true, 60% chance that we're going to do marketing after our R&D, but that will cost us an extra $5,000. So we're going to then look at, here's the 60% chance, and it's going to cost us $5,000. 40% chance we terminate after research and development, in which case we're outlaying $0 on marketing. Those last two outcomes, the 40% chance of a good economy and a 60% chance of bad economy, goes with the revenue for the good economy is that high quantity times the price. And if it's a bad economy, it's the low quantity times the price. So we make our lists of the activity, probabilities, and values. We convert that into a table so it's nice and easy to see. We use pandas to create a data frame. And then we use list zip because that will take our different lists and put them as the columns in the order you specify, activity, probability, value. And then we give those columns names, activity, probability, value. Now for the work that I want to do, I actually want, instead of having an index 0, 1, 2, 3, what I want to do is actually take the activity column and make it the index. So I'm going to take this table here called var, and I'm going to set the index to be activity. So when I do that, as you can see here, I don't have the typical index of 0, 1, 2, 3. Instead, I have the activities as the index. And so that's going to be helpful for me as I create some of our loops and our procedures here, so I can call it by its activity name instead of its index location. Okay, so what we want to do is we want to, now that we have this table here of our activities, probabilities, and values, what we want to do is we want to list out the possible routes, and then we want to calculate that expected monetary value if we go down those different routes. So let's look at how to do that. So I'm going to define here oh my goodness, why can I never remember this word? I keep wanting to say program, but it's not program. What are we creating when we create these? We are defining a bugger. Give me a second to think. I had never been in Python before. Some words I just, you just can't ever, I can't ever remember what they are. And for whatever reason, the word that keeps popping into my head, function. I keep coming up with a P instead of an F. All right, so we are defining a function. Remember here, we're going to create a calculation. We're going to provide a list of inputs. So we're going to create a function to have it help make this decision for us. And then we can do our sensitivity analysis by putting in new inputs into the function and seeing how it changes. Function. All right, so let's go back. Let's go here. All right, so what we're going to do is we're going to define expected monetary value, and we're going to provide it a table. That's this table up here. And we are going to then have that table of information calculate the different paths and the different probabilities. So this is where you're going to create this to match A1 plus A3 plus A5, A1 plus A3 plus A6, A1 plus A4, and just the A2. So let's start with the first one, A1, A3, A5. So what you want to do is you want to take the name here. We're going to take our var, that's our table, and we're going to locate in the table the A1 index, and it's going to return the value. Then we're going to add to that from our table, we're going to do a 3, and it's going to pull the value for this. So it's essentially in this first row going to do minus 10,000 plus a negative 5,000 plus this A5 here. It's already calculated. That's the 35 times our high quantity of 3,500. Okay, so here's one route. Our second route here is A1, A3, A6. So we just repeat that same code, but locate A1, A3, and A6 and pull the values that go with each. Okay, then we have our third path, which is going to be our A1 and A4. And then we're going to have our fourth path, which is going to be just A2. Then what we're going to do is repeat those, but have it give us the probabilities instead, and we multiply the probabilities. So this will tell us the probability of the first path, the second path, the third path, and the fourth path. So what we're doing is the same kind of calculation that we just showed here, which is A1 plus A3 plus A5, and the probability of that route is 7.2%. So we are creating this function that is going to show that information. Now, what we want it to do is we want it to then ultimately figure out the total expected monetary value of this situation. And so we're going to take our path 1, and we want to multiply it times the probability of path 1. So if we make path 1, path 2, path 3, path 4 into a list, and probability of path 1, probability of path 2, probability of path 3, probability of path 4, a list, then we can use NumPy here to multiply the two. So essentially, it's linear algebra here. We're going to multiply it, add them all together. That's going to get us the estimated monetary value of the whole thing. And then what we would like it to do is not only provide us that estimated monetary value here, but actually tell us the path in terms of the total cost for each path and the probability for each path. So show us all of those pieces, and so that we can look at, especially if we do a sensitivity analysis, what's happening to each of those paths. So we create this function here, which is going to be highly reliant on your decision tree. So you need to know how to take a decision tree and turn it into a function, okay? And then once we have our function, we can then call it. So we're going to call EMV var, and we are going to then have it output all of these components. So this list here of outputs needs to match what you're having it return. Because when it returns it, it's going to return this number, then this number, then this number, then this number. What you're doing is outside of that function, giving it a name. And so you want that name really just to match the name it had inside the function. Okay, so if I do that, and here I am then going to say, okay, well then take all of this and let's give it a name, all those pieces. Let's call it EMV underscore complete. So what I see here is that the estimated monetary value is 10,212. So when we look at this endeavor itself in terms of the whole product and the risk associated with it, the whole project itself gives us a value of $10,212. That's looking at the fact that there is a 7.2% chance that we'll make $107,500. There is a 10.8% chance that we're going to make $34,000. There is a 12% chance that we're going to lose $10,000 and a 70% chance that we'll make $0. So based on the weights of these different outcomes, the estimated monetary value of this whole project is 10,212. Okay, so it's a weighted average of the different possible outcomes that we could encounter. So if we're trying to decide, should we do this project or not, we can see right here initially that it is worth it. Because even though there is a chance that we do research and development and we cancel the project, or we go to market it and then cancel it, that still the money that we put into it in terms of research and development and in terms of marketing, we actually make that back in all likelihood plus more, right? So that's why this end value here of 10,212 is we recoup the cost of the R&D and the marketing in most cases and still made $10,212 total after that. Okay. All right. So let's look at, in this case, we would do the project. Okay. Let's look at some sensitivity analysis. So the idea here is that while the whole project is worthwhile doing based on all our current assumptions, how sensitive are we to what's happening here? So we can look at how much is the decision affected by a change in the assumptions. So let's start with the scenario. How much does decision making depend on the quantity sold and whether that quantity sold is for the good economy or the bad economy? So what we're going to do is we're going to take our function that we built and we're going to look at multiple scenarios. We can look at different prices. We can look at different quantities. So for example, we're going to get this graph here that shows the expected monetary value of the project depending on the price. And here we have the expected monetary value depending on the quantity. And I totally switched up these slides because this is the graph for price and the words for quantity. And these are the questions for price and the one for quantity. So, this should go here. Oh my goodness. Absent-minded professor. Can I use that term? I think that completely defines me. My brain's working on too many things at once. Can't keep things straight. All right, so we'll look at the assumptions we make about price and the assumptions we make about quantity. So let's take a look at the Python code. All right, let's start first by looking at changing the quantities. So we're going to do a sensitivity analysis and we're going to say, okay, well, what if the quantities we're predicting that we sell are not what we had expected? So what we're going to do is we're going to look at what if they are the quantities, so 100% of what we had originally put. And then let's look at what if it's only 95%, 90%, 65, 55, 50. We'll look at a range. So we're looking here that, okay, well, what if the quantity sold is much worse? It's much lower than we had anticipated. How does that impact our decision and would that change what we do? We're going to keep the price here at 35. Okay. And we're going to run our assumptions. We are going to create this empty list called EMV_COM. So we're going to, just like we did before here, create this answer to our question about what's the expected value and what happens at the different paths. So we'll create an empty start. And then we're going to create a loop. Okay, this loop, and you can do whatever for I, for X, for sen in sensitivity, whatever you want to call it. So here for X in sense, for our sensitivity loop here. So this sense here matches that sense. And then it says X here, that X is going to be this here. So what's going to happen is that we're going to look at what if our quantity is 3,500 times 1. So what if it really is 3,500 and 1,400 for low? But also, what happens if it's half that? If it's half of 3,500 and half of 1,400. So we're not changing the price here, we're just changing the quantities. Now in the rest of the loop, what we're going to do is we're going to take our activities, our probabilities, and our values. So that values, this is where the outcome of the economy is good. It is quantity high times price, quantity high, quantity low times price. Okay. Within the loop, we are going to actually have it create the table and reset the index. And so that way it can build a new table for each scenario with the different percentage of quantity. And then what we're going to do is we're going to have it run our function. Notice we don't have to define the function in the loop. We define the function up here. So once you have your function built, then you can call it within your loop. So we're going to call it, okay, here, our EMV var from the table it just built. Then it's going to output X, which is going to be that sensitivity level. And then it's going to output our, where to go? Oh, it's going to output the expected monetary value, the different paths. This is the same as before. And then what we're going to do is that we're filling in this empty list here with all that information, plus what we're going to do is put the sensitivity level. So if we run this loop here, then what we're doing is we're creating this list. Actually, let's just take a look at it, and then we'll turn into a table so it's easier to read. But we can do EMV_com. And what you'll notice here is that we have 1 for 100% of the quantity. And then the first row here should match what we had when we just did our one run with our initial assumptions. But then it has another list, another list, another list at the different scenarios. Well, this is hard to read, right? I mean, that's just a bunch of gobbledygook. So instead what we can do is turn it into a table. So then we take our pandas, pd.dataframe, and we take that EMV_com, and then give your columns names. So this is where you can take, part of this probability in the paths, and the EMV value. You can just copy all that, put quotes around it, and then add maybe the first column called sense for our sensitivity. So the benefit of doing it this way is that then we can see a nice table that shows, for example, if the quantities are only 50% of what we had anticipated, then the expected monetary value here of the whole project is $3,156. So the question is that worth it for our company? I mean, it is positive. The first path, the good economy, gives us an revenue of $46,000. The second path, $9,500. If we quit right after research and development, it's always minus $10,000 after you spend that. Okay. Path 4 is quitting before even research and development happens. So that's always going to be a 0 return. So we can see here what's changing is the positive and negative economy. And you can see here the probabilities. We haven't changed the probabilities in the sensitivity analysis. We kept them as fixed. And what we were changing was the quantities. So you can set it to change any part of your formula and see what happens. And so we'll look at this and say, okay, well, as long as the price is $35 and the probabilities really are what we had set, then even if the quantity sold is half that, we're still making $3,000 to do it. So we can show this on a plot. So we import matplotlib.pyplot as PLT. We're going to use a bar chart. So the kind equals bar. The x-axis is going to be our sensitivity. That's here your percentages of your quantity. The y value is going to be that expected monetary value. Our x label we'll call percentage of quantity. Our y label we'll call the expected monetary value. Notice here we haven't specified anything about the legend. You can specify that you shift the legend outside of the graph. If you tell it to do nothing, then it will put it in, because if you don't tell it not to, it will just do it. And then it will put it inside the graph. So as long as it's not covering things up, we're okay with it like that. So it's not going to run because I haven't imported it first. Import matplotlib, now run it, and we get that chart. Okay. So in the next video, I'll cut this one here. We'll look at what happens if we change the price.